All right, here we go. So today we're going to learn about the concept of rolling. All right. So I guess two main learning points here. So a rolling object is both translational and angular motion. So in other words, it's moving both linearly and angularly. All right. In order for an object to roll on a surface, you have to have friction. Okay. Well, I guess I shouldn't say that. In order for it to undergo smooth rolling, you have to have friction. All right, and then what we will see is that there are two ways that you can use to sort of consider the rotation. You can either choose the pivot point at the center of mass or at the point of contact. All right, and you really ought to be familiar with sort of both of the options because depending on the circumstances, sometimes one method of solving the problem is easier than the other. All right, so with that in mind, here we go. All right, so first of all, a definition. What is called a smoothly rolling object, all right, a smoothly rolling object is one which is rolling with no sliding occurring between, the rolling object and the surface that it's on, okay? So the motion of a smoothly rolling object can be thought of as a combination of both translational motion and angular motion, okay? So if you think of a wheel, so as a wheel, rolls across the floor, two things are happening. One, because it's rolling, it's got rotation, right? So if you forget about the fact that the wheel is moving linearly, and you just picture sort of a wheel spinning in space, right? So the idea in this little drawing here is it's spinning, what's that, clockwise, I guess, right? So the idea is a point at the top edge of the wheel is going to be spinning forwards with some velocity, and a point at the bottom edge of the wheel is going to be spinning backwards at that same velocity, right? And then a point at the middle really has no velocity because it's staying stationary, right? So that's a result of just the rotation, okay? Now, if we now just consider a wheel, so imagine a wheel just like literally just floating through space. So it's moving, it's not rotating at all, it is literally just moving forwards, okay? Like, here, I will draw it. So here's our wheel, right? Here's the spokes of the wheel, right? So here's our wheel just kind of floating through space. Notice it's not rotating at all, it's just moving, right? And so what happens there is now every point on the wheel is moving forwards at the same velocity, right? Cool? Now, it turns out that if your object is rolling, then the velocity of the wheel as it moves forward is kind of equal to the velocity of the center of mass. Okay, so when we talk about v, for a rolling wheel, so here's our wheel and it's kind of rolling forwards, right, rolling forwards. So the velocity of the wheel is the velocity of the center of mass. Okay, but because it's rotating, technically the velocity of the different points on the wheel is different, right? Okay. So if you consider vector addition, okay, for each point on the wheel, all right, so let's do this. So the idea is if the wheel is smooth rolling, then it's undergoing both pure rotation and translational motion. In other words, it's rotating and moving forwards at the same time, okay? And so the idea is at the center of the wheel, there's no rotational motion, but there's translational motion. So 0 plus translational gives us the combined effect of both, right? Now, consider a point at the top of the wheel. So the point at the top of the wheel is moving forwards because the wheel is actually rotating, but it's also moving forward because the wheel is moving forward, right? So we've got forwards motion there for two different reasons, because the wheel is rotating and because the wheel is moving. So you've got a velocity of v plus a velocity of v means that the point at the top of the wheel is actually moving forwards with a velocity of 2v, okay? And then down here at the bottom where the wheel is touching the floor, the idea is because there's no slipping, I'm getting ahead of myself. So due to the rotation, this point is spinning backwards relative to the ground, right? Okay. Due to the translational motion, it's moving forwards. So here we've got negative v plus positive v, and they cancel out. The idea is relative to the ground, the velocity of this point is 0, okay? Because it is not sliding at all, right? That means that this point can't be sliding across the ground, so there's no motion at that point, okay? So, I guess, how do I want to say this? So when you consider what's going on, there are two ways that you can solve these problems, okay? Option one is if you consider your pivot point being the center of the wheel, that gives you one option, okay? The other option is to consider your pivot point at this point here where the contact with the floor occurs, okay? So I want you to kind of keep in your head the idea that relative to the ground, the velocity of this point is 0, okay? And I'll kind of show you another way of thinking about it, okay? So the whole idea is when you think of an object rolling, you can think of it as simultaneously spinning and moving linearly forward, okay? And that's kind of what this drawing is trying to illustrate for you, okay? Now, this picture, I don't know if you can see this. I'm hoping that on the notes these turn out better, like on the printout of the notes. Let me embiggen this so you can see it maybe a little bit better. So what we've got here is you've got a wheel. And this is a, whatever, a prolonged exposure, I guess, right? So the idea is here's our wheel, okay? I don't know if you can see, but down here you can actually see the spokes, okay? And that's because those spokes, they're moving slowly, right? But up here, because the points at the top of the wheel are moving at such a high speed, the spokes at the top are moving so fast that they're so blurry you can't even see them, right? Okay, so that's the intent behind that drawing, is that the farther you go down the wheel, the slower the spokes are moving, and therefore sort of the clearer they show up in this picture. Okay. All right, so the other way to think about the rotation, and I think that this explanation will sort of solidify why this velocity down here is 0, is instead of considering it rotating about the center of mass, let's consider it sort of rotating about this point. All right, so imagine a box. All right, so we've got a little box. All right, and it's so this is like Fred Flintstone. He's got square tires, right? And so the tires are rolling about this point, right? Okay, so the idea is, okay, so they're like, hey, we built this car and it's got square tires. That was dumb. Why don't we build a tire that has 6 sides? Boom, 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 right? Or 8 sides. Boom, right? Or infinite sides, right? So the idea is when you tip this square wheel over, there's no motion at this point. It sticks, right? Adding more sides just means that sort of each fall is sort of smaller, right? So the idea is if we consider, in these first 3 drawings, you can see, oh, this wheel's tipping over. Oh, this is tipping over. Oh, this is tipping over. Oh, this is tipping over about this pivot point, okay? And if you think about it that way, that then makes it clearer that, okay, well, the velocity of this point is 0. And then as you get farther away from that point, your velocity gets bigger and bigger, okay? So those are kind of the 2 ways of thinking about rotation, okay? You can think of it as a combination of linear and translational motion. When you do that, you're thinking of the center of mass as your pivot point. Or you can think of it as exclusively angular motion, in which case you consider the pivot point to be right here, okay, at the point of contact, okay? So great, so that's sort of the idea of sort of how we can process this. So how do we use that to solve problems? All right, so let's go back to that first method where we consider the center of mass. All right, so what we're going to do in these examples is we're going to find the acceleration of an object rolling down a plane inclined at an angle of theta. All right, so this angle here is going to be theta. Okay, and we're going to assume that the object has a rotational inertia of, and I'm doing it generically, it's just going to be beta times mr squared. So maybe it's a disk and it's 1/2 mr squared, or maybe it's a sphere of some sort and it's 2/3 mr squared, or whatever, right? But you've got some fraction, some beta times mr squared. All right? So what we're going to do here is we're going to calculate the acceleration of this circular object rolling down our inclined plane, okay? And so in option 1, we're going to consider it as rolling about the center of mass. And so what I'm going to do then is, here's my center of mass, that's going to be my pivot point, okay? So pivot equals center of mass, okay? So with that in mind, we need to start by making a free body diagram, all right? So what forces are going to act on this thing? Well, the first force is gravity. Force of gravity equals mg. I'm not even going to split it up into components because I'm feeling lazy, all right? Now, we know that there is, you know what, I will split it up into components. Actually, that's why I have 2 circles on my drawing here. So if we split it up into components, sorry, then you've got FG perpendicular and FG parallel, all right? Cool? And so we can find those. So this one's going to be, what? mg times the cosine of theta. And this one's going to be mg times the sine of theta, all right? Okay, cool. So what other forces are there? Well, there's a normal force. All right, so our normal force occurs at the point of contact, and we know it's got to cancel out our FG parallel. So here's our normal force. So that's going to also be mg cosine theta. I don't know if we need to put it over here on this other drawing or not, but I'll do it just for the sake of completion. Oops. All right, let's see. All right, and then finally, there has to be friction, right? Because otherwise, the wheel would just be sliding down the hill, and that's not what's happening. Okay? So there's got to be some friction. It's got to be static friction because it's not sliding, right? So right here, we've got force of friction static. Now notice, it's not necessarily going to use the maximum amount, okay? So we can't write that that's equal to the coefficient times the normal force. So maybe that's worth noting. Okay, it may equal it, but it doesn't have to, okay? All right, and then we can go over here and do the same thing. The only reason I'm making my arrow so big is just so that you can kind of distinguish between the arrow and the surface there. So here's our static friction. Okay, so there's our free body diagram. Okay, so now remember, our pivot point is right here at the center of mass. Okay, so our goal is we want to find the acceleration. So what we're going to do, we're actually going to solve this the same way we dealt with stuff in the last video. We're going to set up a net torque equals net torque equation and a net force equals net force equation. All right. Okay, so I'm going to focus on this drawing over here. Okay, so let me do this. I'm running out of room. So we're going to go 2 screens, insert a blank page, go back to full screen, here we go. Okay, so if I do net force equals net force, here's what I get. Let's see. Mass times acceleration equals, well, let's see. My FG parallel is pulling in the direction of acceleration, minus friction is working against the motion. But I don't know what friction is, so I just got to leave it like that, right? Okay, and then notice my normal force and my perpendicular component of gravity, those guys cancel out, right? Okay, so that's one equation. But I've got 2 unknowns here. I don't know the acceleration, and I don't know the force of static friction, right? Everything else we know, okay? So the other equation I'm going to make is this. The net torque about my center of mass has to equal the net torque about my center of mass. So if I consider this as my pivot point, notice the only force that's actually going to produce any torque is the static friction, right? So I times alpha equals the torque from friction static, okay? So notice, if this is my pivot point, shoot, I need to go back to, yeah, I need to go back to full screen, don't I? Let's see, dig in this. All right, so the idea is, here's my pivot point, right? So for normal force, the normal force is perpendicular to the lever arm, right? The lever arm would be like this, normal force is this way, So they're, I'm sorry, parallel, right? So the normal force doesn't produce any torque because it's just pushing right back through the pivot point. Gravity has a zero lever arm because it's at the center of mass. So only static friction is actually going to produce torque. Okay? So here we go. So let's see, what is I? I is beta times mr squared. And then alpha, remember we did this last time. Remember, alpha, we can use a jumper equation and write that as A over R. So this is A over R, okay, equals the torque from static friction. All right, and so my torque from static friction, is the force of static friction times my lever arm, which is just my radius, right? And notice that static friction is perpendicular to the radius, okay? All right, so let's see. So if I multiply both sides by r, let's see, basically all of the r's here cancel, right? Because here I've got r squared over r, which is r, and then that r cancels this r. So all of the r's cancel. So this blue equation becomes beta times, oh, I just changed, I guess it doesn't matter. Becomes beta times mass times A equals force of friction static. So now I've got two equations and two unknowns, okay? So let's solve this thing. So, oh no. So I think if I just do a substitution, if I replace FFS up here, then I'm good, right? So now my new equation is MA equals mg sine theta minus FFS, but FFS is beta times MA. So if I add beta times MA to both sides, I get MA plus beta, MA equals mg sine theta. The m's all cancel. So this is A times 1 plus beta equals g sine theta. So A is just g sine theta over 1 plus beta. There you go. That's the acceleration of a thing rolling down an inclined plane. All right. Now, you need to be able to derive this. All right. And more importantly, what I want you guys to understand is you're going to be running into all kinds of situations where you've got things rolling. In this one, it happens to be rolling because gravity is pulling it down around. Okay, but that's not the important part. The important part is how I solved this. All right. I solved it by setting up two equations. Net force equals net force. Net torque equals net torque. Okay? And that's how you're going to attack all of the problems on your homework assignment. Okay? Now, so this is method number one. So everything that I did here was done assuming that my pivot point was this center of mass, right? Okay? But that's not the only way to do it. All right? And in fact, I might be going out on a limb here, but I think usually this is the harder way. All right? I think that option 2 is usually the easier way. So I guess I would start with that frequently. And if it doesn't work, maybe come back to option 1. All right, so let me show you option 2. Here's how option number 2 works. Ooh, too many blank pages. All right, let's see. We got to get back to single page. No, not what I wanted. Undo, undo. There we go. Boop, boop. Okay, so I'm going to go back and I'm going to make the same three-body diagram I had before. All right, so we've got our FG parallel is mg sine theta. FG perpendicular is mg cosine theta. Normal force is mg cosine theta. Friction. Okay. So what I'm going to do this time is I am going to consider a different pivot point. So this time my pivot point is going to be the contact point. Okay? So here's my new pivot point. I'm going to label it with a big fat P for pivot point. Okay? So now, let's see. So again, my net force has got to be 0. Right? So that net force equation is going to be the exact same one that I had before. Where is it? This guy, right? So we have this same net force equation, right? But again, there's two unknowns. I don't know my acceleration, and I don't know my force of static friction. All right? So, but check it out. What I was saying before is when we do it this way, kind of what we're doing is we're thinking of this thing as perpetually tipping over. So there's always angular motion about that pivot point. So let's write an expression for the net torque about that point. This is really neat how this one works. All right, so check it out. So let's see. So the net torque about my pivot point is equal to the net torque about my pivot point. All right, so you got to be careful though. So this becomes I times alpha equals, you know what, I'm going to do this. Well, okay, so I times alpha equals net torque. So check it out. Because my pivot point is right here, friction doesn't produce any torque because it's at the pivot point. Normal force doesn't produce torque because it's at the pivot point. My FG perpendicular is actually parallel to my lever arm, so that doesn't produce any torque. The only thing causing any torque is this, oh shoot, not enough colors. This component of gravity is pulling it over this way and causing it to tip over. Okay? So it's the torque from gravity. That's the only one that has any torque. Okay? Now, the trick is this. So remember at the beginning of the example, I told you that I was beta times mr squared. Remember, that's the rotational inertia about the center of mass. What we need is the rotational inertia about point P. Okay? So the only thing that's tricky about this is we got to use the parallel axis thing. So I about our pivot point is equal to I about the center of mass plus mh squared. Okay? And what is h? Well, h is how far we moved our pivot point from our center of mass. So our pivot point, our center of mass is here. We moved our pivot point down to here, so we moved it by a distance of r, right? So I about the center of mass is beta times mr squared plus m times, well, h we just decided was r squared. Okay? Oh, well, this is just, let's see, this is beta mr squared plus 1 mr squared, so that's 1 plus beta mr squared. So that's my I about my pivot point. Okay? Because our pivot point is no longer at our center of mass, we've got to use the parallel axis theorem. Okay? So that's how we got this. All right, that was in video, I don't know, whatever, earlier video of this chapter. All right, so now I can go back up here and plug all this garbage into this equation. All right, so here we go. Let's go back to 2 pages. Scroll this guy down where we've got everything. All right, so now all I'm going to do is I'm going to use this equation. Here we go. So I about our pivot point times alpha equals the torque from gravity. So I about our pivot point, that's this mess. 1 plus beta times mr squared. Okay? Times alpha. Alpha is just a over r. Equals the torque from gravity. Well, the torque from gravity is the force of gravity times my radius, right? So the force of gravity is mg sine theta, because it's only the parallel, or the parallel component that produces torque, times r. Okay? Using the same logic as before, all of my r's are going to cancel. My m's cancel. And so we've got 1 plus beta times a equals g sine theta, or a equals g sine theta over 1 plus beta. Same answer we had before, which is super cool. All right? So, which method is easier? I don't know. I guess it's a little bit of 601. This one you got to use the parallel axis theorem, but you didn't need to worry about your net force. Honestly, they're both valuable. All right? There you go. All right. So your problems on your homework are going to be kind of a combination of using these two ideas. Will my highlighter work? No, it won't. So it's using a combination of, oh, cool, yay. Net force equals net force, and net torque equals net torque. That's how you're going to solve the problems. All right. And you really just got to kind of dive in and try. All right. So there we go.